ahead and get started. So I am pleased to introduce Roberto Rondanelli, who comes from the University of Chile. He is an assistant professor in the Department of Geophysics in the University of Chile, which is in the capital of Chile, Santiago, Chile. So he's come a long ways to visit us here. Roberto did his PhD from at MIT. He got it in 2009, where he worked with Richard Lindzen. He is, during his time in Chile, he's done a lot of work to try to better understand the weather and climate of Chile. It's a really interesting region, and you'll see that in his presentation. And he will actually be here all week, which is great, right? You don't fly all the way from Chile to be here for only a couple of days. So he'll be here all week. You'll see him around. We're actually collaborating on a project to try to better understand the mechanisms behind the influence of the MJO on extreme rainfall events in northern Chile. So you'll see some of that work here. So yeah, if you didn't get a chance to catch him today, you'll see him around in the hallways, I'm sure, throughout this week. So please stop by and say hi. And with that, I will let you take over.
Thank you, Stephanie. Thank you very much for inviting me. For me, it's also kind of special to be in this place because two of my former professors studied their PhD here at Madison under Professors Letao and Professor Hassenrath, actually. So they were all very excited to know that I was here in Madison this week. And actually, it's not only the people, but the themes are also similar. I mean, Professor Letao and Professor Hassenrath had an interest in the climate of South America from even before in the 60s and 70s. So this sparked interest in our community to come here for PhD, and then I am sort of second generation or third generation of these people studying the Atacama Desert and climate of South America. What I want to present today is actually a case study in which we've been obsessed about for the last 3 or 4 years. It's a very strong event of precipitation that occurred in 2015, during March 2015. And not only that, it was also a heat wave or a warm event in Antarctica as well. So I'm going to talk about these two events in a sort of historical way in which we approached the problem. We saw them as separate events, and then at some point we realized that they were connected somehow. So this will be the way in which I present this. So to put some context, this is South America, and this is Atacama region, which goes from about 18 south to 27 south. And you see here, this is the climatological precipitation. So precipitation is high near the mountains, but those sort of white and blue points are the precipitation in this so-called hyper-arid region, which basically doesn't get any precipitation. It's really, really dry. And during these 3 days in 2015, it got from 10 to 100 millimeters during these 3 days, okay? Which is a lot for this region. And south of the hyper-arid core of Atacama, there is this basin, which is called El Salado Basin, that got the highest amounts of precipitation, about 100 millimeters in 3 days for the whole extension of the basin. So this is a picture of Quillagua, which is the driest place on Earth recorded, which has records, okay? So basically, based on 33 years of data from 1964 to 2000, the climatology of precipitation is 0.05 millimeters, which is very little. I mean, I don't know how to translate that into inches, but it's a lot. It's almost nothing, right? And it fell 4 millimeters during these 3 days, which is the precipitation of 80 years, right? In 3 days. And this is a video taken along the river El Salado, which I show you. This was the basin that was located at the south of the hyperarid core. And this is on day 25th of March 2015. And basically this river is not really a river, it's more like a creek, and not even a creek for you. It will have normally 1 meter cubic per second. That will be the stream flow. So calculations put it into 1,000 cubic meter per second during the height of the event. And it was, obviously, you can see very destructive flood. About 50 people died, and number of people disappeared. And the damage of this storm was $3 billion because it was mostly located in a region which is very strategic for Chile. It's a mining region of Chile. So there was a lot of damage in the industry as well. So it was really a huge storm. So why is Atacama so dry? It's basically a combination of different things. It's obviously because we are in the descending branch of the Hadley cell, but also there is a cooling of the adjacent ocean by upwelling. Winds are predominantly south, so you get cold waters coming out. That means that you have increased stability just because the ocean is so cold, and you are basically in tropical latitudes in the free troposphere. So that gives you a lot of increased stability. Also, there is a large deck of stratocumulus that further reduces the radiation that gets to the ocean, so it gives you more stability as well. But it also prevents humidity to actually reach to the desert. The stratocumulus keep things near the boundary layer, and the topography actually intersects the stratocumulus. So it's basically humidity is trapped in the marine boundary layer. Also, you have additional mechanisms. You have the Andes that heats up during the day. That produces a local circulation that descends over the coast. So it gives you additional subsidence over the coastal region where the hyperarid core exists. And there is also this is more controversial, the Andes prevents water vapor coming from the other side, from the Amazon, for instance, to reach the Atacama. So basically, the combination of all these things give you this basically no precipitation. So what happens when it rains in Atacama? This is the sea surface temperature over the period of 2014 and 2015, and you can see in the red line that during March 25th, the SST reached the maximum. And you know that a maximum SST will give you also a maximum in water vapor just through Clausius-Clapeyron, right? So there was an anomaly of precipitable water along the coast of Atacama. And on top of that, we have this circulation that is called a cutoff low. I'm not sure if you are all meteorologists here familiar with the cutoff low, but it's basically a low that extends to the subtropics from the pole. And what this cutoff low did was to concentrate water vapor along the coast that was anomalously warm at the very height of the seasonal cycle of temperature. At the end, this is the end of the summer, beginning of autumn. So this is the highest temperature that you will get in this region. So that basically, this cutoff low transported water vapor towards Atacama and produced the rainfall. How do we know it rained in Atacama? Well, obviously I show you the video, but if you think about it, there are not many rain gauges in Atacama because nobody will pay for measuring precipitation in a place where there is no precipitation. So how do you do about that? I mean, the station that I show you is actually in a river. It's the main river that flows through Atacama that feeds from the high Andes, right? And it gets there. So the water agency puts a rain gauge anyways, right? So that's why we know that that's the driest place. But for those that like precipitation from space, this is a lucky orbit that we got from TRIM. TRIM decommissioned like in April 2015. This is the radar on board of a satellite. And one of the last things that TRIM saw was the precipitation over Atacama. One of the orbits saw this precipitation, so we know it rained in the hyperarid region. We don't have ground radar either in Atacama, so this is our best image to actually realize that it rained in Atacama. And we wanted to understand a little bit better this rainfall event, so we did some sensitivity modeling studies using a regional climate simulation. And we did the simplest thing that you can imagine. We just used the boundary conditions during the event, but within this domain, we changed sea surface temperature to climatology instead of having this high SST anomaly that we had in the real case, okay? And when you suppress the anomaly of temperature, so when you run your model with climatological SST, precipitation reduces, especially in the hyperarid region. So you basically get, this is percentage-wise, almost 100% reduction of precipitation over the whole region. So there was, I mean, you can, if you want to explain precipitation in Atacama, very simply, you have to say, okay, it was the SST along the coast that gave you the water vapor to be transported by this upper level cyclone. If there were no SST anomaly, then the upper level cyclone will basically be dry and you will not get your rainfall event.
Do you have examples of similar synoptic setups with the kind of normal seasonal SST
Yes.
that don't do that? Oh,
Yes, exactly. Okay. So cutoff lows happen 6 or 7 times per year, and most of them don't do anything.
Okay.
They don't have enough water vapor to produce. I mean, cutoff cyclones are unstable. So if you trigger instability, you can produce convective precipitation. But as long as you have water vapor, if you don't have water vapor, you don't have rain. And that's what we observe here. So basically this showed us the importance of having the water vapor source for this perturbation to produce rainfall. But the same day that the floods in Atacama occurred, and this was what called our attention, there was the highest temperature ever recorded in continental Antarctica, okay? So this is Esperanza Station, which is a station near the tip of the peninsula. And you see that the gray dots are all data of temperature ever recorded seasonally. And the red line is the 2015 maximum temperatures. And you see during this day, the high goes above anything else in the map. Yeah, there is maybe a point here that has a similar temperature in October, but this is basically the highest ever in Antarctica, and is significantly above the freezing temperature. So you would expect a lot of consequences maybe for the ice. We thought it was interesting. And it happened the same day, so maybe there is some connection. And we looked, for instance, at images, satellite images. And the satellite images actually, when you look at this is the March 22nd before the event, and this is March 27th after the event. You can recognize here the tip of the Antarctic Peninsula, here, here. The seasonal ice was pretty plain and well developed before the event, but right after the event you see these huge cracks and all the ice disintegrating, plus some surface melting on the platforms as well. Yeah. The image is not so clear, and we actually got confused in the first time we published this. We got a major mistake. We confused the melting ponds with the shadow of clouds. Somebody pointed out this in a conference when we were presenting. Like, aren't those clouds there instead of melting ponds? Yeah, but we checked the images later and we found melting ponds. So the results stand, and there was major melting event during this episode. So some Dutch colleagues also made a study afterwards. They made a study on intense winter surface melt on the Antarctic ice shelf. And they had a station in an Antarctic platform, which is called Larsen C. They measure the melting. They can estimate it through an automatic weather station that they operate there. And in this paper, they actually focus on the winter melt events, okay? But they didn't realize that their major melting event occurred during March 2015. They don't even mention it in the paper. But actually, this is over the period in which they are analyzing it. This is the major melting event. So there is evidence also from the surface stations that there was melting during this episode. Okay. And we decided then that we should look into more detail on what was the reason for this episode to happen. And we found that it was a fan wind event. So basically, if you are familiar with the satellite images, this is just I think this is infrared image, and if you look into detail here, you see this black region over there, like very narrow black region. That is the called Föhn gap. So this is actually a region in which the air is descending very rapidly after the flow past the topography, and then it descends, and you don't see any clouds there. And this Föhn gap is an evidence that the Föhn is actually happening. So again, we did some more regional climate simulations using this regional climate model, and here we basically also very naively we thought, what if we just remove the topography? Will we be able to determine or to attribute the heating to the actual fan? If we remove the topography in the model, then we don't have a fan wind, right? We just have advection of air maybe from the tropics, so the temperature will increase anyway because it's tropical air that is coming to the peninsula. So we wanted to be able to distinguish between these two processes. And you can see this is a control simulation, precipitation. The rainfall is mostly concentrated on the windward part of the peninsula, and on the leeward part you have very little precipitation. The temperature is maximum during the day, during the 24th, and you can see here that it goes about 14. The model never reaches the actual maximum that was observed. We tried many things. We tried REC-CM, different models. We tried also Polar WRF. None of the models reproduced the maximum, okay? And basically, we just stopped at that. We don't know. Other groups have also looked into this, and they are not able to reproduce the maximum Föhn wind temperature, okay? So if you look at this is a cross section along 66 South, and this is wind velocity in color, and the temperature is in contours, and you can see there temperatures well above freezing over the whole part of the leeward side of the peninsula. Okay, the topography is in gray, and you can see this is where the Föhn gap should be in the image, and you see temperatures of 14 or 16 degrees on the side of the peninsula. This is all glacier ice, okay, in the part of the topography. So during this event, a lot of that ice was very above freezing for 10 or 15 degrees maybe. There are no observations over the mountains to know for sure. And this will be a sort of a Hofmüller plot along this 66 South. This is the control simulation, and you see the increase in temperature well above 14 Celsius around March 24th. When you remove topography, you don't see the increase in temperature. So it was a very simple exercise anyway, but we were able to determine precisely the amount of warmth that can be attributed to the Föhn event. as opposed to just temperature detection from the tropics. And here also the differences between the control and known topography simulations. You see there is a lot more precipitation on the windward side of the peninsula when you have your topography. When you don't have it, then you don't have that much rainfall. And the mechanism for the fan depends on how much rainfall you have on the windward side of the peninsula. The more rainfall you have, the higher the temperature will be on the other side of the topography. Okay, so basically about 95% of the warmth in the control simulation is due to the presence of the topography. So the conclusion will be it's the topography that produced the highest temperature in Antarctica through this fan mechanism. Okay? But then, about the same time, at around the same time that these things happen, a little bit earlier, actually, a few days earlier, it was registered the strongest Madden-Julian oscillation on record. Okay, so people developed this index that is called the Real Multivariate Index, RMM, and they have it from the 1974 or so. So during this day, March 16, it was the maximum on this index. Okay, it was above 4. Never before seen above 4. And the phase of the maximum was phase 7, which is located in the Central Pacific. And we knew from previous research that phases 7, 8, and 1 were somehow related to events of precipitation in northern Chile, not specifically in Atacama, but in northern Chile. And if you look at all the phases, this is the highest event. This is the distribution of the amplitude of this index, which is centered around 1, and very rarely goes above 2, and even more rare about 3, and so. And this is the highest one. And this is a Hofmeurer diagram taken from Carl Schreck webpage. This blue line shows the propagation of an MGO, and this is about the day of the maximum. You see that there is also other kinds of tropical variability going on as well. So each of these envelopes show a different wave. So the blue is the MGO, the black one is the equatorial Rossby wave. So the total heating produced by this event is due to the combination of these different modes of variability, the MGO and maybe the equatorial Rossby. And you can see it in precipitation as well. The precipitation peaks in a region in the Central Pacific a little bit after the MGO event. So what we did was to calculate this wave activity flux, inspired in work by Stephanie and other people, and we basically saw that the wave activity flows out of this region of minimum OLR. This region of minimum OLR in the Central Pacific is located around here. This is the box where precipitation was calculated in the previous figure. And you can see the evolution of the thing from 16th of March to 19th to 22nd to 25th. And by the 19th, you see this sort of high below the poleward of the minimum OLR, and a low over there, and a similar pattern in the northern hemisphere as well. So this quadruple pattern, and maybe an incipient low during this date. And then if you move forward in time, then you see the whole pattern of a high and a low and a high and a low, and the vectors pointing towards the energy moving along this path. Just for comparison, this is an old paper that shows what would be the response of the circulation in the upper atmosphere due to this heating of the MGO, where the heating is actually located. You will expect highs to each side and lows further downstream, which is similar, I think, to this pattern over here and over here. When you look at, there are three different fields here in this figure. There is precipitable water, there is potential vorticity at 300 Kelvin, but just one contour, the -2 contour, and waves at 850 hectopascals. So what you see here is basically this intrusion of very high precipitable water air coming in and sort of following the shape, the general shape of the potential vorticity contour, and the potential vorticity contour being stretched, and the precipitable water following this contour as well. And you can see on the March 2015, on March 24th, that the precipitable water reaches the Antarctic Peninsula, and the wave is breaking. And a sign of wave breaking is the formation of this blob here, which is the cutoff low. So this blob here is actually the cutoff low that produced the rainfall in Atacama. And on the other hand, this anticyclonic breaking is moving forward, moving the water vapor, the precipitable water, along towards the Antarctic Peninsula. We did some calculations of the ray tracing of the Rossby wave. So basically, this is the idea here is to follow the energy of the wave directly. So you pick a point here, which is the point on which you think the wave originated, and you choose a wave number. Why you choose a wave number? Because it's not really precise. The OLR is just a shape, a big shape of heating over the ocean, and maybe you can speculate that it's a wave number 3 or number 4 or maybe number 5, but it has different wave numbers on it. So we try different ones, and actually wave number 4 shows a very good agreement with the actual propagation of the anomalies. Okay. And so we basically think that this MGO, that was the strongest one that ever observed, propagated a Rossby wave out to the extratropics, a Rossby wave number 3 or 4, and it produced both of the extremes in a way. So it gave the necessary moisture for the atmospheric river to get into the Antarctic Peninsula and feed the fan wind with precipitation, high precipitation that was enough to produce the maximum on the other side. This also happened at the time in which the sea surface temperature is highest in the southern hemisphere. Okay, so that's another ingredient. And I just wanted to mention that MGO is still not completely constrained in global models. So Wang et al. Picked a number of CMIP 5 models and look at different statistics for the MGO. And there are some models that do a good job, maybe 4 or 5 of them, and some models do a pretty bad job as well. And the things that they don't represent well are different indices of the MGO, for instance, propagation, but also the vertical structure, in this case, the divergence at the highest level at 200 hectopascals, or the heating at 300 hectopascals. So basically the scale of the waves that propagate is related to the scale of this divergence, for instance. And the divergence in 200 hectopascal is important because that's the source of the Rossby wave that will propagate afterwards. So you would think that if a model doesn't do a good job, in producing the right divergence at 200 hectopascals, then it won't give you the signal to produce a Rossby wave within the model, and therefore you won't have the right propagation of the Rossby wave, and you don't have the extreme. And this is just a thought, but I think models don't do well with extremes. And one of the reasons is that there are still physical processes that are not well represented. So if these extremes, like the ones I'm showing, are due to tropical variability on the synoptic scale, and the tropical variability on the synoptic scale is not there in the model, then the models will have a hard time to actually give you the extremes, not even only in the tropics, but in the extratropics through these teleconnections. So in conclusion, we know these two events now are related, and they originate in this strong just MGO on record. So basically, it propagates a high and a low and a high and a low. So the wave is large amplitude enough to break as well. The forcing is very large, so the wave also breaks. It breaks into this cutoff low that directs the water vapor towards Atacama, but also the atmospheric river that brings water vapor into the Antarctic Peninsula is also patterned by this teleconnection. So sort of, this is the general panoramic view that we have now of the event. These are, we focus on the local and regional sort of explanations first, but now we see that there is a more hemispheric one, and I'll leave you with that. Thank you. Yes, Professor.
During this event, what happened to the water level of Titicaca?
Well, we researched, there were a number of floods here, not only in Atacama, but along the coast, the equatorial coast. This is dry even to the equator, okay?
Mm-hmm.
So the coast is very dry along this part of South America. So I guess, I haven't looked at the time
You haven't
series.
looked at it?
No.
Because it gives a good time, the Titicaca water level is a good long-term time series for climate research.
Yeah, it would be interesting to look at that, yes.
Yeah, it's very, very interesting. I wonder if there was anything of particular anomaly going on in the northern hemisphere in response to this event, and if not, how much of the southern hemisphere sort of subtropical jet, polar jet interaction and the circumstances that allowed this energy to propagate in the direction is really a factor as well. So it's really interesting that it's an enormously strong MJO, but is it conceivable that a similarly strong MJO without the right environment in the southern hemisphere wouldn't have led to this?
Yeah, well, those are nice, very interesting questions that we're planning to tackle at some point. I mean, I feel like I've been doing this research on this case study. These are 3 days, but we already have like 4 papers out of this storm, and I'm not sure if I want to look at the storm again. But there is one thing about the propagation into the southern hemisphere, that you can see that the anomaly is actually not symmetrical. It's more concentrated in the southern hemisphere than in the northern hemisphere. So if you believe these are stream function anomalies. So the stream function anomaly south of the OLR anomaly is actually higher amplitude than the stream function anomaly in the northern hemisphere.
Yeah.
Nonetheless, there is a northern hemisphere response.
Mm-hmm.
And here I'm avenging the southern hemisphere because I'm not showing what is happening in the northern hemisphere.
Yeah. And I don't know what the South Pacific subtropical jet looks like climatologically. Does it have the same sort of behavior as the Pacific jet, extension and retraction as it's leading?
It does, and one of the things that we're doing with Stephanie is actually look at the mean field of wind and see what will be the propagation for these things on top of the mean field. Let me remind you that this is the beginning of El Nino. I didn't talk at all about this, but this is the event that produced the westerly winds that kicked off the El Nino 2015. okay? And then there is a SST anomaly over here that by thermal wind balance will produce an acceleration of the jet in the southern part of Australia. I don't see Australia here. Oh, New Zealand is over there. So the jet will be reinforced here. So that probably played a role as well.
Yeah, okay.
By guiding a little bit the propagation out of the tropics.
Yeah, it looked like the water vapor flux, I don't know what you call it, the stream, the atmospheric river, I think you referred to it,
Mhm.
definitely looks like it's getting a little bit of an acceleration at those longitudes, doesn't
Yes.
it? Yeah, yeah, that's really interesting. Yeah, it's really excellent work.
Yes.
How frequent are atmospheric rivers in the southern hemisphere, and how often are they tied to these extreme weather events? I mean, it's a lot like the Pacific coast of the U.S., where you get atmospheric rivers impacting topography and causing heavy precipitation.
Yeah, I was talking to the students at lunch about this, and basically precipitation in Chile goes from 0 to nobody knows how much here. And it can be 10,000 millimeters, okay? And the reason is that southern hemisphere circulation is more zonally symmetric than the northern hemisphere. So your southern hemisphere jet is very reliable. It gives you rainfall over the same region most of the time. So this is actually the southern hemisphere Patagonia is the hot spot for atmospheric rivers. It's the highest frequency in the world. But basically, they don't go north, and they don't go south very often. They just concentrate there. So to have a warm event in the peninsula, you need the atmospheric river to do this. And for that, you need a very strong wave to produce the meridional forcing of the atmospheric river.
It's funny that you mentioned the northern hemisphere teleconnection, which is cut off, which is what we do all the time to the southern hemisphere.
Yeah.
we just remove the southern hemisphere so that this is probably a little taste of our own medicine to do not know what's going on in the northern hemisphere.
I don't remember anything extraordinary in North America in late March 2015, so it does suggest that the more interesting teleconnected
Yeah.
reactions were in the southern hemisphere to this big event. Certainly does suggest that. Really
Well,
interesting.
of course, it's chance, what location a teleconnection ends up in. So it could just be that it happened in some not very interesting place, right, in the northern
Well, possibly, yeah. Except you usually see some signature that, at least to my eye, I'd remember a big ridge or a big trough somewhere over North America that was unusual. Even if the weather wasn't unusual there in association with it, and I don't remember that. But
It'd be interesting to kind of compare, like you said, look at the jets and see what
yeah,
like.
yeah, it would be really interesting, especially early March. What's going on in the Pacific, South Pacific subtropical jet in the first 15 days of March? Is it unusual as a setup for the propagation to the south?
Yes.
I'm just wondering if you mentioned a local sea surface temperature anomaly. Is that just El Nino for that year? Or I'm thinking in 2013, 2014, 2015 in the North Pacific, there was what they call the blob for the sea surface temperature anomaly. Probably there was something going on at the same time in the southern hemisphere, but I never checked. That often happens. They're both warm all the way up and down. Well, at high latitude coast at the same time, and mid latitude coast at the same time.
Yeah,
Was
yeah.
there any relationship with the northern hemisphere sea surface temperature?
I'm not sure if there was a relationship with the northern hemisphere, but this is one of the problems. I come from a department where there is no oceanographer. Okay, so we have discussed this before, that the circulation below here is very rare. Okay, to be stationary, and the dominant winds here are southerly, that produce upwelling. But if you have northerly wind, you get downwelling and heating. So maybe part of the reason for having this warm anomaly is actually that the circulation was doing it to the ocean as well. So our first idea that this was local and it was just the water vapor there, it might be wrong because the teleconnection is producing this wave, so the wave itself is heating up the ocean. and it's giving the right sea surface temperature to transport the water vapor. And that would require like a couple modeling experiment, right?
And a shallow thermocline. It must be really shallow right at the coast. I mean,
Uh-huh.
in the hundreds of miles offshore right there. So it's really easy to perturb. Yeah, it's really interesting.
Any other questions? Okay, well, we will thank Roberto then.
No, thank you.